Hello ladies and gentlemen, welcome to my lecture series Modern Gauge Theory. This is lecture 2. We'll talk about the field equations and the Noether Theorem. We will derive the field equations in analogy to the Euler-Lagrange equations of motion in classical mechanics, and the Noether Theorem goes back to Emmy Noether, a German mathematician. She worked in Göttingen and had worked out that theorem in 1918. Later, the physicists recognized that it is very important to describe conservation laws in physics. The Euler-Lagrange field equations are derived in analogy to the Euler-Lagrange equations of motion in classical mechanics. The principle of least action is realized everywhere in nature, also in quantum mechanics, in the microcosmos. So we write now for a generalized action integral the following: 2, 1. This is generalized because we have a Lagrange density, because we have here not dt like in classical mechanics. We have to generalize that, and so we have here the differential in the 4 dimensions, because we must work here Lorentz invariant. That should be clear from the special theory of relativity. And here we have now for the independent coordinates, not the coordinates and the velocities, we have the fields psi and the derivatives of the fields d psi here. So, and the variation must vanish. That means delta s or delta, the integral is equal to 0. And now we carry out the variation. That means we have to differentiate L with respect to the independent coordinates, to psi here, and to the derivatives of psi here. And we have to write here delta psi and delta d psi. Okay. Then we apply again a partial integration for the second addend here. According to this rule, that should be clear from calculus. So we identify for that rule, f is here this differential quotient with L. And then the other factor is then G bar, G prime here. And that means, okay, G is the integral of this. That means the D is vanishing here. And we have to differentiate f. So f prime is, the same, but we write here a D in front. That means we have to differentiate this. Okay. Then we can write for the action integral, here to 5. We have a part here out of the integral. At the endpoints P1, P2, the variation is vanishing. So this part vanishes. And here in the brackets we can factor out delta psi. So we get the expression 2, 6 here. And the integral must be 0, and the delta psi cannot become 0. That's an arbitrary value. So the expression in the brackets here must vanish. So we write this, and we have here the Euler-Lagrange equation, field equation, for quantum field theory, in analogy to the Euler-Lagrange equations of motion in classical mechanics. Okay, here we have done that for scalar fields. If we want to do that for example spin a half particles, then we must be careful with the calculation, but we will do those things later in the lecture series. Important is to understand the principle here. So now we want to look at the Lagrangians, the Lagrange density functions for free fields. So we begin with spin 0 particles or scalar particles, scalar fields. Yeah, we know from classical mechanics that Lagrange function is in general the kinetic energy minus the potential energy. And so for free spin 0 particle, we write, yeah, L is equal to, yeah, instead of the velocity, the derivative of the coordinates, we have here the derivatives of the fields psi. And we have psi and psi star, that is the complex conjugated one. And we have minus, okay, the potential energy, if we want to call that with that, that is the energy of the particle because of its mass. That means we have here mc divided by the Planck constant, and we have psi and psi star. That results from energy is equal mc squared. That should be clear from the relativistic quantum mechanics. And to have less to write, we use the convention that is usually used. We say, okay, c and speed of light and h, Planck's constant, is equal 1, and so we needn't to write those constants. So we get for L here this to 9. And yeah, this is, we can say, the generalized kinetic term. Okay, it's not identical with the expression in classical mechanics. Okay, now we substitute L in the field equations. That was this. Now we calculate the two addends. We have for the derivative of with respect to psi, this, and in the second term this. And now here we differentiate with respect to psi. So that means because these are independent coordinates, the derivatives and the psi itself, that we don't get anything from this first addend here. We only get something from this one here because we differentiate with respect to psi, so psi is cancelled out. And in the second part, okay, we didn't get any thing from the second addend here because we differentiate with respect to the derivatives of psi here. So we have this result here, and that means if we factor out psi star here, we have this. And we can do the same for the non-complex conjugated psi. So the same here, we have here psi star now. And then we get the same, but here we have the function psi, and in 211 it's the complex conjugated one. And this is so-called Klein-Gordon equation for spin 0 particles. And the two states psi and psi star represent the two states of a charged particle. So we can consider the pi mesons. So we could say the psi star is a pi plus, and the psi is a pi minus particle. And to represent a particle with neutral charge, with no electrical charge, then in this case we have psi star is equal to psi, and that means for the psi 0 particle we have to set psi is equal to psi star. Okay. Then spin a half particles. For free spin a half particles we have the Lagrange function to 15, this one here. Here we have to apply the Dirac theory. That should be clear from relativistic quantum mechanics. And here we have psi bar. That is the so-called Dirac adjoint. Psi bar is the psi function, psi plus, multiplied by the gamma 0 matrix. This is the shape of the gamma matrix here. And here we substitute again in the field equations. Here are the field equations again. And if we differentiate with respect to psi bar, then we would cancel out here this psi bar, and the rest remains in the formula here. So we get this one, and so we get the Dirac equation for spin a half particles here to 18. That should be clear from the lecture series in relativistic quantum mechanics. Then the next spin 1 particles or vector particles. We have for the Lagrange density here this expression. And now we will have practice in tensor calculation. We have here two parentheses which are multiplied with each other, and for spin 1 particles we have this characteristic expressions like derivative minus derivative, or here another kind of derivative minus derivative. So if we multiply the two parentheses, then we have 4 dents here in the brackets. The first and the fourth term are identical because we see we have here two scalar products, mu and mu as co- and contravariant index, and we could exchange the names of the indices here. Instead of nu we can write nu, and instead of nu we can write mu, and then we have exactly the same like here. So that means we have this term twice. And yeah, the same with the second and third term. We have here identical scalar products in these two terms, so we have that term twice. And so we can factor out a factor 2, and that means we haven't, instead of a quarter, we have a half here in front. No, and we have now this shorter expression 221. Then we have to substitute L in the Euler equations here. So we first have to bring the indices in the right form. So instead of d mu c nu contravariant, we write here covariant indices alpha and beta and use the metric tensor to pull these indices down here. That should be clear from here, tensor calculus. Okay, and then we can write here, instead of here delta mu contravariant, we write here this expression GG and d alpha psi beta. And we do that for the second term here in 221. We pull the contravariant indices down with the two metric tensors, so we get 224. Now here we have the differential quotient. We have to differentiate now with respect to the derivatives of psi. And so if we consider here the first term, then this is the same like here. That means this is vanishing and we get this. But we have to use here the product rule of differentiation, and here we have also got the same expression but with other indices. And with the rule here that if we have different indices, then we have Kronecker symbols with the indices here. That should be clear. Then we get instead of d psi alpha beta, we have now here two delta Kronecker symbols. And we do the same here for the negative term here. We can eliminate now some metric tensors and some Kronecker symbols again. Okay, what is happening here? We have here alpha and here alpha mu. That means this this becomes contravariant mu. Then here beta covariant, here beta mu contravariant means mu contravariant. Here if we have here alpha mu, this Kronecker symbol, then this alpha would become a mu, and if we have here mu and mu are contravariant, that means this mu becomes contravariant, and so we have this expression here 226, and yeah, here we have identical terms. These two positive terms are identical and the two negative ones are identical. That means we can cancel here a factor 2. Okay, then we get only this easy expression here, 226. And we have for the other term in the Euler-Lagrange equation, if we differentiate with respect to psi, to the fields, then that means, the great term here with the derivatives is vanishing, because we have to differentiate with respect to psi and not the derivatives of psi. Now we have only this easy term here. Then we have here a co and a contravariant index. So we push this contravariant index down with a metric tensor here. And so we can write here this. We use the delta Kronecker to make out of the new index a new index. That means we have here psi mu squared, and if we differentiate this, we get a factor 2 in front. So here there is no factor a half in front. This cancelled out, and then we can eliminate the g and the delta, and so we have this one here, this expression as the second addend in the Euler-Lagrange equation 227. And then if we use both parts, then we get for the Euler-Lagrange equations this one here, 228. And now we apply another differentiation, d mu. If we do that, we get here another d, and here we solve the parenthesis. So we write here d mu in front of the first term, and the order of the differentials doesn't make a difference. So we write the d mu now here in front of the psi directly. And here we see that we have here a scalar product and here a scalar product. And that is the same like here and here. So this term and this term are identical. And then we divide by m squared. And though we get d mu psi mu is equal 0. And so we can write here for spin 1 particles 230. This one, that is another writing for this here, for 228. And the second equation here, 231. Then this 230, that is the so-called Broca equation for spin 1 particles. That should be clear from relativistic quantum mechanics. And here we have 4 components, but we only need 3 independent components. So we have here an additional condition. And so indeed we have 3 independent conditions for here spin 1 particles. Yeah, if we compare that with the Klein-Gordon equation for particles with no spin, we see yeah, the only formal difference is that we have here an index, that we have here, yeah, vector, we can say. Yep. And if we have massless particles, for example, the photon is a particle with spin 1, but with no rest mass, then yeah, m is vanishing, and so we have only this wave equation here for spin 1 massless particles. And that means we have only 2 independent components. Yeah, that's what we need for photons. Okay. Then spin 3 half particles. Yeah, in nature we do not find any fundamental particles with a spin 3 half. And so, yeah, we only want to consider that shortly here. We have as a Lagrange function, here it is, 233. Yeah, it is similar to the Lagrange density of spin a half particles. And we then get for those particles the Verita-Schwinger equation. Yeah, this one here, 235. Or there is a shorter, easier representation. Here, this one, 236. Here we see that is, we can say the Dirac equation, but here, yeah, we have an index that is the same like if we make a transition from 0 spin particles to spin 1 particles. Okay. Then spin 2 particles. There is only one elementary particle that have a spin of 2, the graviton. That is a mediating boson of the gravitational interaction. And yeah, we must say until now there is no working gauge theory for gravitation. We will consider that problem later in this lecture series. So for now we look at the equations for spin 2 particles here. Yeah, we can do that in analogy to spin 0 and spin 1 particles. For spin 0 particles we need only one independent component. For spin 1 particles we need 3 independent components, and of course for spin 2 particles we need 5 independent components. So a 4 vector has only 4 components. So here usually we write a tensor with 2 indices. That means this is a tensor with 16 components. So, but of course, because of the symmetry here, psi mu nu is the same like psi mu nu. We have only then 10 independent components in the tensor, and with the condition that this scalar product must vanish in analogy to spin 1 particles, then we have instead of 10 only 6 independent components then, and with this condition here to 40, another scalar product, we have only 5 independent components. That is what we need for a spin 2 particle. Okay. Now I want to present the very important Noether Theorem. The pronunciation is Noether because it's an eigenname of Emmy Noether, a German mathematician. She had worked out that in Göttingen, Germany. In general, we have a symmetry if a transformation leaves something unchanged. And if we have a symmetry in physics, then we know the result is a conservation law. That should be clear from classical mechanics. If we have displacement in space and time as a transformation, then we get the conservation laws for energy and momentum. And now we want to consider that for quantum mechanics in a very general way. We start with the action integral again here, and we will consider general transformation, and the Lagrange density or the formalism must be invariant under the transformation. And so we begin here. The general infinitesimal coordinate transformation can be written as here 242. The old coordinate goes over into the new one, x prime. And we have the old coordinate plus the displacement of any kind. Then we want to use the parameters delta omega, and so that we have for the displacement delta x here, the matrix Y, and the dimensionless parameters omega, delta omega. We can say a delta x that is an arbitrary continuous transformation. Okay, in the space-time coordinates we can have a translation or rotation. And of course the fields psi, they depend on those coordinates, space-time coordinates. And so they are also transformed then. Okay, then first we can write psi goes over to psi primed in the new coordinates. And this is simply written the old psi plus the transformation. Okay. Then this delta psi, we can write that with the same parameters omega. They're the same displacement here. So yeah, this displacement depends on the parameter. So we write delta psi is equal to here a capital Y multiplied by the parameters 245. Y, the capital Y here, that's another matrix than the small y matrix. Now, the delta psi here, that is the total variation of the field psi. And so we can write only for the transformation in the fields delta psi, that is the transformed psi minus the old psi, this one. Or we can write for the total variation, now this. So that means that we have here the two variations, the variations in the coordinates, from x to x prime, and the variation from psi to psi prime here. Here psi prime, and here x prime. So we can write for the change in the psi function. We differentiate that and multiply that by the delta x, norm variation. And this delta psi, that is only the variation in the fields here. And then we can continue to write now this 248. We can write for the delta psi, this variation. We differentiate with respect to the transformation parameters omega, and have then delta omega. And we use the expression for delta x. We had to write here y and the delta omega parameters. So we have here this expression 248. And now we consider a complete variation of the action integral. Now that means we write delta s, and then we know that from the Euler-Lagrange equations that we have to differentiate with respect to psi and the derivatives of psi here. But then we have a dependence of the coordinates. That means we differentiate with respect to the coordinates x, then delta x. And we also have the differential, and so we write here delta d4x for the variation of the differential d4x. Okay. Here we have got three parts. And we consider the last part here, the variation of the differential. For the differential, we have according to coordinate transformations, that should be clear, we can write for the new coordinates the old one, the 4 vector, and use here the Jacobi determinant. Or you can write it in this way. It's the old, if we multiply by 1, that would be a Kronecker delta, no change. Yeah, plus and 1 plus the change. And the change is the differentiation of the x-coordinates here with the delta. And then we can easily write 1 plus d mu delta x mu d4 x. And for the change in the differential delta d4x, then we have here this second part. That means d mu delta x mu and the old d4x here, 251. And now we can write everything again in one integral, because in each part we have now d4x again. Though now we use the Euler-Lagrange equations here to substitute here this differential quotient dl d psi by the other expression in the Euler-Lagrange equations here. So we set in here this. Then the other things stay there unchanged. So we have 253 here. And a differentiation and a variation are commutable, so we can exchange a variation and the differentiation. Here in the second addend, we could write instead of delta d mu psi, we can write d mu delta psi. And so we use the inverse of the product rule for differentiation. If we look at here the first and the second addend, we see in the first addend, this differential quotient dl, d derivatives of psi, is there with a differential, and here we have a psi or a delta psi with a differential, and so we can write now for these two addends only this one here in 254. If we apply the product rule of differentiation, then we would have differentiation of this multiplied by delta psi, that is this one, or as the second part we have this dld here multiplied with the differentiation of the delta psi. And we use the inverse of the product rule for the other two addends here. Here we have the differentiation of L, and here we have the differentiation of delta x. And so we can write here this here in 254. And then we can write here this in one integral. If we multiply out the differential here that is applied to the first and second addend here. So then we substitute the variation delta psi. So that means for delta psi we get the delta t the total variation minus the expression with the delta x, and so we set in here this expression for the delta psi. Now we substitute the variation of psi, the total variation, and the delta x then, and so we get here the y matrix. So we have here now the y matrix, and we have, instead of the delta x, here the small y and delta omega. So here we have now in all the addends the delta omega parameters. That means we can factor out them. So we have here 257, and the action integral shall be invariant under some transformations. So this means the variation delta s must vanish, and so we must say, okay, the delta omega cannot vanish. These transformation parameters have any value, so the great parenthesis here must vanish. So that means the derivative of this whole expression here is 0, and if the derivative, especially with the derivation with respect to time coordinate, is vanishing, then that is a conservation law. And for this expression we use the letter n. This is the so-called conserved generalized Noether current. Okay, but the Noether tensor is defined with opposite signs, so we have here changed the signs, this minus instead of plus, and so on here. So this is now the Noether tensor 259, and if we integrate now over the space, then we obtained the conserved Noether charge, generalized Noether charge. So then we have only one index, and here we have only the 0th component, and so this means then that we have here only the time component. That means the derivation with respect to time is 0, and this is a conservation law. And this is very abstract, so we consider some examples for conserved quantities. First, perhaps energy momentum. Here we consider a translation in the space-time coordinates. And so we can write for the transformation, the old coordinates are now the new ones by addition of a vector, 4 vector, so we have a displacement in all the 4 coordinates. And yeah, this is a outer transformation in the space-time coordinates, and now inner transformation. So there is no variation in the field psi. So the new psi function is equal to the old psi function. No change in the fields itself, themselves. Then we have for the Y matrix, only the Kronecker delta, and we identify the omega parameters as the A vector here. And yeah, because there is no inner transformation, so the capital Y is 0. Now we substitute now in the Noether tensor here, and then we have now here if we consider 259, this is vanishing, and now we set in Y here in these 2 terms. So we have this expression 263. That means, we have now here the Kronecker deltas in both terms here. And we can here write then instead for the new index here, contravariant, J index here, that is this here, and so we get this result. And if we think of what we have learned in relativistic quantum mechanics, this is the energy momentum tensor. So here we have to add the Hermitian conjugated, of course, or if we have only complex field, then the complex conjugated here. This term is treated in complete analogy to the first one here. Perhaps a remark. It is delta nu J is equal to the metric tensor in co and contravariant, the co and contravariant index. And if we want to write the complete contravariant version of the tensor, of the energy momentum tensor here, we have to write this. So, and here we haven't got a delta, we have a G. So, and now again we integrate over space. That means we sum over all the momentums, and so that means the change is 0 in time, and that is now the conservation law of momentum and energy energy is the zeroth component here in the vector P. Okay, then next example, the angular momentum. Now we apply as a transformation infinitesimal Lorentz proper autochrome transformation. That should be clear from the special theory of relativity. And here we have epsilon. This is an antisymmetric tensor, so we have a minus if we exchange the two indices. And yeah, we identify now as the delta omega parameters here epsilon. And yeah, here we have two-dimensional matrix if we describe a rotation, and though we have an additional index here in the formalism, and that means we have to write here for the Y matrix now 3 indices. And of course then in these two indices for the transformation it is antisymmetric. Okay. And now we subtract here 268 from 267, and then we have the two expressions here. We have the expression with y and epsilon here, and we write the factor 2 to the other side. We have twice epsilon and x here. And now we will have practice with tensor calculation. We can write instead of 2 epsilon this sum. Then because of the antisymmetry we can here write minus and exchange the indices. Then we pull this index up to a contravariant index with a metric tensor here. Then we multiply the metric tensor into the parenthesis. And now here we have a scalar product in nu. And yeah, we can use any index for this scalar product. So we write now here beta. And here we have a scalar product in nu in the second term here. And we use instead of nu alpha here. Yeah, and we exchange the alpha index here in the nu index. Okay. Then we can write this. Here we write an additional Kronecker symbol because we want to have here an alpha index in the epsilon tensor. So we must write this, and the same in the other epsilon tensor here. So here we have the same epsilon tensor in both terms, so we can factor out the epsilon tensor. And then we have this expression. So this means that the Y matrix is this expression now here, this in 272. And the transformation of the fields we can write in analogy. This here we have the epsilon tensor, and here we have an index more, because for rotation we have 2 indices, and for only a translation we need only a vector with 1 index. So, and now here we choose now the y as the product of another G matrix and the psi fields here. And of course we have here antisymmetry in the 2 indices mu and nu. And the transformation of the field psi depends on all components in general. Though we have to count over these components by j here. Okay. So we can now obtain for the Noether tensor. This is the Noether tensor in the general form, and now we have here instead of 1, 2 indices, alpha and beta, and then we have here 3 and here y with 3 indices. And if we now substitute the y matrices, then we get this expression 277 here. This is the small y, and here we have the capital Y exchanged by G. So now we write the terms in another order. So we write now this. That means we have here factored out the brackets here. And so we have now these 5 dens. And now we eliminate the Kronecker deltas and the metric tensors. So here this Kronecker delta means we have, instead of this nu, an alpha index, or this G means we have, instead of this contravariant gamma, now a covariant beta. That is what we find here. And so on. And so we have got here this expression 279 for the Noether tensor. And the energy momentum tensor we had derived, we see it here again. We see here this is an energy momentum tensor multiplied by x beta here. And here we see this is also an energy momentum tensor multiplied by x alpha. And so we have here this first term with capital G here, plus this is a positive one, plus this energy momentum tensor multiplied by x, and here the other one So, and so we get the conservation law for the angular momentum. We have then the matrix M, which is a negative of n, and here the derivative of M is vanishing, and so we have again a conservation law, in this case for the angular momentum. And now an example for internal decrease of freedom. We had in the other examples the transformation in space-time coordinates. No, we make only a transformation in the fields. That means we change the phase of a complex field psi. So this time, we have no coordinate transformation, so the small y is 0. And we have for the transformation in psi, this gauge transformation, we can say, we have here the complex e function, and we multiply the psi with that complex e function and the parameter omega. Okay, this is the change in the phase of the wave function. We say omega that is infinitesimal small. And so we can write a Taylor series, or the first terms of a Taylor series, the first two dens. Then we have this here, means 1 plus I omega psi. 1 is the old one, plus and I omega psi, that is the change of the wave function, we can say. Then here, obviously, the capital Y is now I omega, I psi, and though we get now for the Noether tensor a very easy expression now. We have here this with the small y's here and the capital Y, that is the general expression, and now the small y's vanish, and we substitute only the capital Y with only one index here, because there is no change in the coordinates. And though this is here a very simple Noether tensor, and if we add the Hermitian conjugated here, then we can write now for the current J, this, that should be clear, this is a current, and the current is conserved. And so we have the conservation law here for charge, because we can make an integration over space, and what remains is the derivative in time here, and and the derivative is vanishing, and so we have a conservation law for charge, the electrical charge of particle or system. Now we finish lecture 2. Next time, in lecture 3, we will talk about the gauge theory of the electromagnetic interaction. Thank you for watching. See you next time. Goodbye.